Okay, one last final illustration about Newton's third law. Now we talked about action-reaction forces. Let's take, for example, this little plasticware lid, and I'm going to punch it. I think I've got anger issues. When I exerted a force on the lid, remember it was essentially stationary, all of a sudden, boom, it accelerated, didn't it? In fact, it accelerated quite a bit. Well, why was that? Because I exerted a force on it, right? I exerted a certain force. I'll call it, let's see, force of punch. And that was the same, didn't you remember from Newton's third law, the force that I exert on the lid must be the same as the force that the lid exerts on me, correct? So, therefore, the force of punch, let's say the force of the punch on the lid, I'm going to put FPL, has got to be equal to the force of the punch on my hand. I'm going to put FPH. That's Newton's third law. Now, let's talk about the acceleration on each of the objects. Let's talk about the acceleration. So remember, from Newton's second law, a net force, and the only force that was acting on that lid really horizontally at least was the force of my punch. That's what caused the acceleration. Well, why did it accelerate so much? Because it was the mass of the lid is really, really tiny. So I'm going to make a little m there, and then I produced a large acceleration. I'm going to make a big old lowercase a here. The acceleration of the lid. All right. That, remember, Newton's law is F equals ma. So essentially, I'm just rewriting the force of the punch on the lid as being the mass of the lid, which is tiny, times a huge acceleration of the lid. And remember that the force of the punch on the lid must be equal to the force of the punch on my hand. However, what happened to my hand when I punched it? Not much, right? My hand continued, it was moving along at a certain velocity, and it essentially continued along in that same velocity. It may have slowed down just a little bit. Well, why was that? Because my hand is much more massive. So in this case, the mass of my hand, I'll make that big old M of my hand, only experienced a small little acceleration. Yet notice that if I have a big mass and a small acceleration, that can give me the same product as a small mass and a large acceleration. Okay. So another interesting thing is that Newton's third law applies to forces, contact forces, like punches and pulls and frictions and all that kind of stuff, but it also applies to forces at a distance. For example, gravity, right? I hold my, my apple up. I let it go. Well, what's going on there? Why does the apple fall to begin with? Because there's a force of the earth pulling on the apple that we call weight, right? So the earth pulls on the apple with a force we call weight. But didn't we just say from Newton's third law that you can't have one force without another force? So if the earth pulls on the apple, doesn't the apple pull on the earth? You betcha it does. So then you might ask yourself, well, why do I see the apple? And I understand from Newton's second law that, okay, the earth pulls on the apple, and that means there's a force there, and in fact, it's an unbalanced force, and that's what causes the apple to accelerate. In fact, I can figure out the acceleration of the apple by, so acceleration of the apple is equal to the weight of the apple. Again, we're not really considering air resistance at this point, divided by the mass of the apple. Again, this is going to be Newton's second law just rewritten. So, well, what's the weight of the apple? Isn't that just the mass of the apple times g? And of course, I'm dividing by mass of apple, and so you can pretty clearly see that yes, my apple should fall at an acceleration of g. That makes sense. However, shouldn't my earth accelerate as well? Isn't my earth being acted upon by a force? What if I look at the forces acting on the earth? Well, in this case, I say, okay, well, let's see, what's the acceleration of the earth? I'll put A with a little e there. Let's see, the force is the force of the apple acting on the earth, which is the same, remember for Newton's third law, for every action there's an equal and opposite reaction. So the force that the earth pulls on the apple with, downward, which we call weight of the apple, must be equal to an opposite in direction as the force of the apple acting on the earth. So it turns out that my numerator here, the net force acting on the Earth, is still the same. It's essentially the weight of the apple divided by the mass. Now it's not the mass of the apple, it's the mass of the Earth, because I want to figure out the acceleration of the Earth. And so we wind up with, we rewrite the mass of the weight of the apple as mass of apple times g. But now notice we're not dividing mass of apple by mass of apple. We're dividing the mass of the apple by the mass of the Earth. And you can figure out the mass of the apple compared to the mass of the Earth is such a tiny fraction. That's why essentially the acceleration is so small that it's negligible. You couldn't see it, you certainly couldn't measure it, much less see it. And that's why Newton's third law still is upheld in this situation, but we're dealing with the same force acting on really different masses. The mass of the Earth is so huge that the acceleration of the Earth is essentially negligible.